m1 is moving towards right, let's say with speed u1, and the other particle is of mass m2, let's denote it with a green ball, and it's moving towards right with a velocity u2, let's say mass is m2. Suppose we have two particles. Now we see that the vector shown here, u1 vector is shown a bit greater in length. This means speed of the rear particle that is moving behind the first one is greater. So when speed of this particle is greater, collision will take place surely. Collision will take place. So we see that u1 is greater than u2. This means collision will surely take place of these two balls. Let's say collision is elastic. We are considering the collision is elastic. Now what happens? Let's see. So this is the condition of these two particles immediately before the collision. I am not saying that these velocities are before the collision. The velocities are immediately just before the collision. So these are the velocities. Now let's see what happens immediately after the collision, just after the collision. So it is not given, we are not given that the collision is head on, so we cannot straightforward see the motion of these two particles in a particular direction. We can guess the direction. Let's see the first particle that is shown in yellow color. Let's see, this particle is moving in this direction with some speed v1, making some angle, let's say beta, with the initial direction of motion. And the other particle, which was shown with the green color, is moving in this direction with speed v2, making some angle with the initial direction of motion, which is alpha. So this is the situation just after the collision. Now we have to analyze this situation, the event in center of mass frame. In ground frame, we know that if we want to calculate v1 and v2, then we have to apply momentum conservation along the let's say horizontal axis or the x-axis in this direction, and also we can compare linear momenta in y direction, and this will give us two independent equations, and the other one will be obtained using energy conservation, kinetic energy conservation, which will be the third equation, right? So still we are left with one more variable. Just after the collision, we have to calculate four variables: v1, v2, alpha and beta. You can see here. So we don't know beta, we don't know alpha, we don't know v1, and we don't know v2. So we need to know four variables just after the collision. So we have simply three equations. Two equations obtained by applying conservation of linear momentum in x direction. Let's say this axis as x and the other is y. So the other equation is obtained using conservation of linear momentum along y direction. So two equations from there, and the third equation is obtained using conservation of kinetic energy of the system just before the collision and of the system just after the collision. So we need to know the fourth parameter, the fourth condition. Of course, we need to know the fourth condition which will be given the question. Otherwise, we cannot solve this question specifically. But with some conditions, we can find some specific results. We can find. Before that, I want to emphasize that let's see what happens when we see this collision from center of mass frame. This means if observer is located in the center of mass itself. So let's see, center of mass of these two particles are located somewhere here. This is center of mass. So velocity of center of mass can be calculated using the formula. So this is initial velocity. So I write this as u center of mass. this can be calculated m1 u1 plus m1 m2 u2 divided by m1 plus m2. So this is what is called as velocity of center of mass. And if I consider these two particles as a system, then there is no external force. As there is no external force acting on the system, this means what? The velocity of center of mass is not going to change after the collision or just after the collision. So this is also velocity of center of mass, not exactly, which is exactly equal to the velocity of center of mass before the collision. So now we have calculated velocity of center of mass. Now, if I am observing the situation from center of mass, then we need to know what is initial velocity of one with respect to center of mass. So this is equal to u1 minus u center of mass, which is equal to u1 minus m1 u1 plus m2 u2 over m1 plus m2. Now, this can be simplified as m1 u1 cancels out, and this is m2 u1 minus m2 u2 over m1 plus m2. This is initial velocity of one with respect to center of mass. Initial means just before the collision. So this is equal to m2 u1 minus u2 over m1 plus m2. If we need to calculate initial linear momentum of one with respect to c, we will multiply what? This is a vector quantity, so we need to write vectors. As we have shown in the example, we have taken the case where all the particles are moving along positive x direction, so we can skip this notation. We can skip this notation without loss of generality. There would be no problem if I don't show vector sign just before the collision, because all the particles are moving towards positive x-axis, and we can write plus for positive x, minus for negative x. We don't need to write vector sign here. So this can be written, this is equally valid. So momentum of first particle is equal to mass of first particle and speed of first particle with respect to center of mass. Whether you can write it or not, this is completely your choice. There will be no effect on the result. So as long as vectors are shown in a particular direction, you can skip this notation of vector sign over the symbols. So what happens now? Let's see. If I multiply, this is m1 m2. So this is what is called as linear momentum of one with respect to center of mass. Now what we see that we can also calculate initial velocity of 2 with respect to center of mass, which is equal to u2 vector minus u center of mass. As all velocity vectors are in positive direction of x-axis, so we can skip the vector sign. So we write u2 as u2 and uc as m1 u1 plus m2 u2 over m1 plus m2. So if we simplify it, what we get? We get m1 u2, and this is m1 comes common, and this can be written as u2 minus u1 over m1 plus m2. Similarly, we can write linear momentum of 2 with respect to center of mass initially, just before the collision, very simply multiplying mass with this. So mass of 2 is m1 m2, this is u2 minus u1 over m1 plus m2, m1 plus m2. So what is more interesting? What is the first interesting result? When we observe the collisions from center of mass frame, we are going to get a very interesting result, and the result is that we see here that what is P1C? You can see just what is initial momentum of first particle just before the collision. So initial momentum of first particle with respect to center of mass is given as P1C initial. This means this was equal to, you can see here in the previous slide, this is M1 M2 over, this is M1 M2 over M1 plus M2 into U1 minus U2. Okay. Now similarly you can find momentum of C with respect to center of mass just before the collision, which was equal to M1 M2 over M1 plus M2 into U2 minus U1. What we see? We see that, very interesting result, what we see that if I take sum of these two terms, then P1C vector plus P2C vector, we see this is equal to 0. This is very important result. Means this is the sum of momentum just before the collision. This is just before the collision. This is just before the collision. So we see that if the sum of two vectors is equal to 0, this means these two vectors are equal and opposite. So whatever be the direction of motion of particles, when you see, suppose two particles are moving in this direction. So let's say one particle is moving in this direction and the other particle is moving in this direction. Let's say this is in this direction as it was explained in the example. So it was first particle with mass M1, mass M2. So if I see this event from center of mass, so the two particles which were originally moving towards right, both particles are moving towards right in same direction. If I see these two particles from center of mass, then surely these two particles are moving in the opposite direction, because the linear momentum of these two vectors is equal to the sum of these two vectors is equal to 0. This means what? The vectors are equal and opposite. So we can straightforward write here that this is the motion of particles with respect to ground. So if there is an observer located on the ground, this observer sees this, observes this, the motion of these two particles in the same direction as from the ground. But what happens in the center of mass frame? So if I am watching this event in center of mass frame, what I will see, suppose I have placed myself in center of mass frame, then if I see this particle is moving in this direction, then the other particle will move in this direction, and the magnitude of these two vectors must be equal. So this is initial linear momentum of first particle with respect to center of mass, and this is initial linear momentum of second particle with respect to center of mass. So this is the first conclusion that we have drawn from the discussion, that whenever we see a particle colliding from center of mass, then the velocity vectors, the momentum vectors, not the velocity vectors, the momentum vectors of the two particles will always be equal and opposite. This must be confirmed in your mind, and it has to be memorized, and it has to be comprehended properly. So what we see here, that this is the case. Now as we see that linear momentum of system is going to be conserved. This means if initially let's say P1C plus P2C is equal to 0, this means the final just after the collision also these momenta, sum of these two momentum must be equal to 0. This means if I write just after collision as dash, so P1 dash plus P2C dash is equal to 0. This is the collision as sum of momentum was equal to 0 before the collision, then just after the collision sum of linear momentum must also be 0, right? Because this is there is no external force, there is no external impulsive force acting on the system, then center of mass, the sum of momenta must be equal to 0. This means just after the collision also, if I see from center of mass, frame, then if this particle is moving in this direction, then the other particle will move surely in the opposite direction. So this is the case. So this is for velocity of particle just after the collision with respect to center of mass frame, and this is the momentum of particle, not velocity. You can see if momentum is in this direction, velocity is also in this direction. So this is equal to, let's write it as P1C dash vector, and this is P2 dash vector. So what is first conclusion? First conclusion is that whatever be the direction, if I see the moving particles from center of mass, the two particles will move in opposite directions, right? And the vector sum of linear momentum of these two particles will always be equal to 0. In ground frame, this may not be 0. This is non-zero. Of course, this is non-zero. In most of the cases, this is non-zero. But in center of mass frame, in every case, this has to be 0. This is the first conclusion that we